there's a couple logistical items. The first one is that we're going to post homework 2 today. It's just waiting on. Oh yeah, thanks. So yeah, homework 3 is about to go live, and we'll give it 2 weeks, which is usual, which ends up being the Tuesday before Thanksgiving. I understand that people have other things in life going on. And so if that becomes like really not reasonable, I'm totally fine with pushing it till like after Thanksgiving, but let's try the 2-week thing and see how it goes. You know, keep me in the loop. I'll just give you a quick rundown of it so it's on GitHub. It should go, I think I'm just waiting for Anthony to hit the go button. So this is question 1 is pretty light. It's like a review of Newton's method. The reason we're doing this is some stuff we're going to talk about next week, I think, so this is just like standard multivariate Newton's method, stuff we've been doing, you know, to like solve the implicit equations for midpoint and stuff like that. And then, so here we have you like solve a constrained optimization problem, which is where we're going kind of last time and today. So this is like KKT conditions where you have an objective function and you have a constraint, and you're minimizing the objective subject to the constraint where you get a Lagrange multiplier, that whole business, which we kind of talked about, you know, a couple times in the class. So we're going to have you do that explicitly right here. And then the last piece, so yeah, that's this one, right? So you got a constraint, you get the Lagrange multiplier deal, you got to build a KKT system, all that good stuff. So that, and then the last little thing in here, which is actually kind of, we still have to do, is we're going to talk a bunch about quaternions. So we did a little bit of this earlier in the class. We're going to do it again in the context of like maximal coordinates, rigid body dynamics, multi-body dynamics with joint constraints and stuff like that. So I'm going to make you do this with quaternions in here. And this is just a warm up round. So that's question 1. Question 2 is really fun. Has anyone ever heard of the rope trick? This is like a, okay, so the idea is, it's an n-link pendulum. I'm doing it, making your life easy here and making it like just 3 links. So it's a 3-link pendulum. And it turns out that if you take this thing and shake it up and down by the base, it will stand upright without falling over. This is a really wild, this really works, by the way. I did this as my like quals project in my first year of grad school. I made one with just a single link with a jigsaw. If you like just shake the base of the inverted pendulum, it stabilizes the upright equilibrium, which is wild and cool. I have a video that maybe I'll show at the end of class of me doing this 10 years ago on my front porch, which is super fun. Anyway, so it works with like arbitrary numbers of links. It just gets harder to do with more links. They call this the rope trick because in the limit of like, you know, large n links, it becomes like a rope. And like in theory, if you take that, it should still work, right, with a rope in theory, but it doesn't actually work, but it will work with like a fairly large number of links. So we're gonna have you do this with 3 links. So this is a 3-link pendulum. We're gonna talk about this stuff, which is kind of coming up. So this is kinematics, blah, blah, blah. We have you do the manipulator equation for this, write it down, sort of simulate it just falling over and doing the chaos, you know, flail all over the place thing. And then we have you do it with the base shaking up and down later on here. Let's see, blah, 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 blah. So yeah, there's animations. That's kind of fun. So that's the like, you know, unstable, just normal thing that you expect. And then we have you do this with the moving base. And so this is kind of fun. There's some tricks in here where you can do a time-dependent Lagrangian. So you don't actually have to model the shaking as an input force. You can actually just model it as like the Lagrangian being a function of time, which is kind of a slick little trick that, you know, isn't that common. So we have you do this, derive it with the shaking bottom thing. And then there's some fun little nuggets in here. So this is it shaking and it stays up. This is kind of wild. So then the last little piece of this is something that I think I've mentioned maybe in passing, but I want you to prove that this thing's actually stable. So we do the dynamics, you see that it's stable. And then I want you to like do this sort of eigenvalue test to show that it's stable. And this is a little subtle here. Normally when you do this, you take an equilibrium point, you linearize, take the eigenvalues, right? We've talked about this. Here it's a little weird because it's shaking up and down, and this is a periodic motion. And it turns out like what you have to do is basically linearize the full period motion around one full period of shaking to get this to work. That's called so this is for a periodic system. This is called the monodromy matrix. So it's like the discrete time A matrix around a full period. So like, this is a kind of a good little thing to know about. So I'm gonna have you do that, check the eigenvalues, and then you can prove that it's stable by showing that the, all the eigenvalues of that like one period map are modulus less than one, right? Like the same kind of discrete time stability. So that's that one. This is a really fun, like, I don't know, anecdotal thing that I think it's cool. And the last one is contact stuff, which we're going to start talking about today, where I'm going to just have you do a brick, a 3D brick, and then throw it and like have it hit the ground and like whatever, bang into the ground, slide. So that we're not going to do friction in this because it's just, I'm going to talk about it in class, but I'm going to, because the problem's already kind of too long. So it's just going to be impact force. So we do Newton-Euler stuff, and then like the, the variational integrator stuff, which we're going to talk more about today. Inequality constraints, which we're going to talk about today. And then you basically just put all that together, pose it as a big optimization problem. We're going to talk about that today. Solve it with IP-opt, which this is all boilerplate code that's already provided that should work, that I debugged last night, because it, of course, broke after a year of package versions changing. And then, you get to like visualize this thing, which I won't do here. But yeah, basically it's a visualizer, like 3D animation. You can toss it from and have it like tumble around and stuff. It's kind of cool. Okay, so that's homework 3, the last homework, 2 weeks from today, which is the Tuesday before Thanksgiving. Make an effort, try, it'd be cool if we got it in before Thanksgiving. I'm anticipating there will be some, whatever, we can talk about it. So any questions about that? Ooh, we got. So that's homework 3, the last one. Basically, this is a sort of a, really simple, like this is almost a gimme. This shouldn't take you very long. The rope trick one's got some meat to it, and the falling brick one's pretty gnarly. We're going to talk about the stuff you need for the falling brick today, basically. And then the rope trick stuff we're probably going to get to like next week. So we should get everything in before, like in the next 2 weeks. It should work out. I have a plan. We'll see if that all works out. Okay, cool. So any questions about that? Last homework, 2 weeks, live today, the usual deal. Everyone cool with that? Okay, then the next sort of order of business is to talk about the project. Okay, so deal there is we're going to do project presentations the last week of class. It's going to be the Tuesday of that week. And then we're not going to have class on the last Thursday because I'm going to New Zealand that day for Coral. So no class the last Thursday, class the last Tuesday, and that'll be presentations. Ground rules are, I have to like look at the timing, but it's going to be like 5 to 7 minute sort of time slot. So like a little bit more than a lightning talk, but not like a very long talk. Kind of like think about it as like 5 minutes plus Q&A. Don't go too crazy with like jobs of like, don't try to stuff all the technical content into 5 minutes. That's not how to do it. And the idea is you want to kind of lay out the project, the problem, why it's cool, and some like tentative results. I don't expect you to have everything done by then. I expect you to kind of like give a sort of standard, kind of 5 minute conference presentation type thing. It's okay if you're still working on stuff. Then, okay, that's the last Tuesday of class. I think that's what's the 6th, 5th or 6th? 6th, yeah. So 6th, come ready to do that. We'll kind of go through them. There's not too many people and groups this time, so it shouldn't be a big deal logistically. So just bring your laptop ready to plug in. I won't make you like upload them to Google Slides or anything because it shouldn't be too tight for time. And then the report, the idea for the report is it's supposed to be in the style of like a standard 6-page, IEEE format, like ICRA or IROS type paper. So like kind of standard robotics conference, 6 pages. Yeah, I'm not going to be a huge stickler for the length. Usually in conferences where like, it's hard to get it that short. Sometimes in the class we have the opposite problem, but like, roughly 6 pages is what we're looking for. Just put it in like the standard LaTeX template for IEEE conference. If you have any concerns about this, just go to like the ICRA website from this year or the IROS website for this year and like get the template. It's pretty easy. It's already in Overleaf. If you use Overleaf, you can just click, like there's a template already in there. It's pretty easy. And the idea is to model this on a standard kind of robotics conference paper. So it's the idea for all of you PhD students is that you can kind of like, get a conference paper out of this and like, polish it up a little bit and submit it somewhere and not, have this be a giant waste of your time. Let's see, what else? So if you have questions about like how to do that, if you haven't written a conference paper before, come talk to me. But I can send you there's many examples. Like go look at the conference proceedings for like the last IROS or whatever that was last week, if you're curious, what they generally look like. But it's, the standard kind of like abstract intro, background section, the meat of your thing, some cool simulation results, conclusion, fit it in 6 pages. That's kind of the idea. Again, plus or minus half a page is fine. Not like going to be super big sticklers on the length or whatever. Okay, any questions about that? Oh, and the final thing there is the deadline for that is going to be, I don't know if I've posted it yet, but I'm going to make it basically as late as I can. So it'll be like 2 or 3 days before my grades are due, is the idea. So it'll be like the end of finals week kind of deal. And I'll get you an official date. I have to go look at when my grade deadline is, and I'll basically back up from that 2 or 3 days. So I'm gonna give you as much time as I can. The sort of corollary to that is you absolutely have to get it in by then, because otherwise I won't be able to get you a grade into the system and there will be a bad result. So that one we can't sort of have too much wiggle. It's got to be like basically there plus or minus a day, or I can't upload your grades. So it'll be like the very end of finals period. Okay. And that should have all the stuff in it, on top of that, I'll be doing like lots of kind of project consulting office hours the last couple of weeks through, into the finals week and stuff like that. Also, in general, if you ever have questions about anything, just Slack me. I think that's sort of a given also. Hopefully you guys figured that out and we can just talk whenever. Okay, I think that there was a lot of logistical stuff, more than usual. Are there any questions, comments, thoughts, concerns about any of that? Anything in general? Stuff we've been talking about? I feel like we've had like a really long, weird sort of not being around kind of thing the last few weeks. Okay, cool. On that note, if everyone's satisfied, we will return to our usually, your normally scheduled programming. Okay, cool. So what did we do last time? So I'm like pretty psyched about this. This is like the fun stuff in here where it's like, this is all the stuff I'm into that usually is not covered in any other classes of this flavor. So hopefully this is, you get something good out of this. Last time we kind of did this variational integrator stuff a little bit more. I basically filled in a few little gaps for you. So we talked about this like discrete Legendre transform thing, which is how you get momentum and velocity out of these integrators. Basically how you properly calculate the velocities on the knot points, right? So that was kind of important and useful if you want to spit out velocities and stuff. We talked about how to do constraints in these things. Specifically equality constraints, right? So like joint constraints. And I posted like the actually working code and and stuff. So you should play around with that. I did like the pendulum in maximal coordinates where it's like modeled as like a point mass in 2D with a length constraint. And if you do it naively with the kind of DAE stuff, it drifts and basically the pendulum mass, kind of starts to drift off into space. If you do it with this stuff, it kind of just works the way you expect. Okay, so we did that stuff, kind of useful. And then we did external forces, non-conservative forces, is like friction, control inputs, et cetera. Anything that's not coming from a potential. And that's obviously important in robotics and super useful. So that's kind of, filling in these little loose ends on that variational integrator story. So with all that stuff, you can now kind of handle, most things you would encounter in a robotics context. Let me do that. So now what we're going to do today is dig into this constraint story a little more, but now we're going to do inequality constraints instead of equality constraints, which is extremely unusual. You will not see this in like normal classical dynamics stuff. And this is how we do contact dynamics. And I should say the we is a small we. This is not how the field at large does it, but I will argue to you and hopefully convince you this is like the correct way to do this from like a theoretical perspective and numerical perspective. it basically slots into all the stuff we've been talking about. You just do inequalities in it and it works. So we're going to talk specifically today about impacts. And then I'm not sure if we get to friction today. We might have to do that next time. See how this goes. All right, so let's start at like a high level. Who's done this stuff before? Who's messed around with like simulating contact stuff in robotics, like walking, grasping? Have you used? Yes. Okay, yeah. Yeah, so a hybrid formulation. Has anyone used like Ujoko or Bullet or any of these? So these are all doing this, you know, internally in some way. We can talk a little bit about this. So I would argue this is basically like at a very deep level, one of the maybe 2 or 3 core reasons why robotics is hard. Like this is one of the major things. So why is this hard? So let's see. Let's like think in our heads right now about a falling particle. So just like a point mass, right? And it's falling and hitting the ground. And for now, no friction. Okay, so the first thing I want to sort of plot is, let's just plot the position of that thing versus time. So we've got something that looks like this, say t, this is the z height, and it's like a little, you know, projectile motion, whatever. So it's some kind of like parabola looking thing, and it's going to do this. And then there's going to be an impact, you know, here, and then it's going to, you know, stay on the ground, whatever. That seems, so if I drop this thing, right, it's going to accelerate under gravity. It's going to whack into the ground and then sit there. That's kind of the idea. Let's now plot the velocity. Kind of in the same sort of picture. So that's going to look like, so let's say this is z dot versus t. So let's say it starts at rest. It's going to accelerate, right? So the slope of this line is going to, you know, like minus 9.8. And then at this moment of impact, it's going to, if we are assuming like actual idealized rigid bodies, it's going to basically do that. Right, if I think about this, so what's going to happen, it's going to have whatever, you know, g delta t, however long it was falling, right? That's this velocity here, minus g delta t or whatever. And then when it hits the ground, it stops, right? There's this big impact, and all of a sudden the velocity goes from whatever this was to, in the vertical direction, to 0. If we assume like idealized rigid body inelastic impacts, this is a jump in discontinuity in the velocity, where it just sort of all of a sudden instantaneously in like, you know, infinitesimal time goes from whatever to 0, right? That seems bad, and like it might cause problems in a number of ways, right? Does anyone have any thoughts on like what's actually going on here? Like in real life, if I do this, I mean, this is a reasonably good approximation. Let's take a random object. That did a little bounce, but like that's actually pretty close to the model. And maybe if I drop it, like, yeah, I mean, that's doing something really, really quickly. It's changing its velocity vector like pretty discontinuously when it hits the ground, right? What's actually going on there is there's internal deformation in the object, right? And there's like energy dissipation happening in like at the material level, right? But all of that is happening insanely fast on like a way, way faster time scale than the like everyday rigid body dynamics, right? So like when we interact with this stuff, think of your robot, right, interacting with stuff, we're maybe reasoning on the time scale of like seconds or maybe tens of milliseconds. The dynamics associated with that, the deformation, in the material is happening like orders of magnitude faster. So from like the perspective of our robotic simulator or like our robot controller, those things really do look like this, right? Like, so the time scale which this stuff is happening in the material deformation, et cetera, that's actually like causing this energy dissipation, it's happening over orders of magnitude faster timescales that we basically can't resolve with our sensors and our simulator. So this approximation of that's happening instantaneously is an approximation, but it's a reasonably good one in the context that we live in, right? Where maybe the fastest controllers on our robot are running at, maybe a few hundred hertz or a kilohertz. This is still happening, like 2-3 orders of magnitude faster than that at the material level. So it's like way, way too fast for us to resolve with anything on our robot. And so this is really what it does look like to us practically and to our robots. So that's like kind of the way to think about this. Okay, so let's sort of keep the party going with like a couple more higher derivatives. So we just did velocity. How about the acceleration? What does that look like? So if we do, time, anyone tell me what this one looks like? Yeah, so we've got like a minus g over here, right? And then at the instant of impact, what does it do? Yeah, it's going to look like a giant spike. So depending on your background, you might call this an impulse function or a Dirac delta function, right? So that's sort of bad. And then if we think about, okay, so this is like your acceleration, say, so this is like z double dot, and then sort of by extension, we can think, closely related to this, we can also think about the normal force coming from the ground, right? Is going to look, it's MA, right? So it's going to look sort of like this. It's going to look like 0 while it's in the air. And then all of a sudden at this impact, it's going to do this giant, impulse delta function thing. And then after that, when it's sort of, at rest, it's going to look like, plus mg, right? Okay, so does this all make sense, everybody? This is like very cartoony, but like pretty intuitive, I think. So the key idea here is that, like, if we're trying to write down F equals ma and reason about this, both analytically from a calculus perspective and numerically from a computational perspective, you could think about maybe ways of dealing with this stuff. Oh, this is like this at this level of positions, this is kind of okay. This curve is, like C0, it's continuous. This guy's kind of bad, where it's got a discontinuity, but at least everything's finite, right? This stuff, on the other hand, is horrible. You've got these like giant, like theoretically, these things are infinitely tall and infinitesimally skinny. So this thing has like infinities in it. It has like, super skinny, impulse spikes. And again, in reality, that's actually got some width to it, but the width is maybe on the like microseconds time scale. It's like 10 to the minus 6 or something like this. It's way, way too fine for us to like ever resolve with our controllers, our sensors, et cetera. And then the normal force, similarly, super tiny spiky things that are going to infinity here over super tiny time scales, right? All that kind of badness. So we really can't do this in a computer, nor should we try to. I mean, that's a bad idea. And there's actually like very fundamental calculus difficulties associated with this. So at the most basic level, if I try to write down F equals ma here, that's fundamentally reasoning about this is the F and this is the A, right? And these guys have these horrible like infinity things going on. So like from a technical, just like basic calculus level, F equals ma is like ill posed here. It's like not well defined, and there's some really, really like deep issues here. In fact, like from a like super formal fancy math perspective, you're like not allowed to write down F equals ma for stuff like that. What you end up with is this other kind of thing called a measured differential inclusion that can like reason about these weirdo infinity jump things. So like technically speaking, the math is even just sort of at a basic level hard here, and you can't write down F equals ma. So let's sort of try to write some notes down about this. So impact, and it turns out also sticking friction, Coulomb friction, which we'll talk about later, cause these velocity discontinuities. For real rigid bodies, for ideal this leads to infinite forces and accelerations. Seems bad. And then sort of in the strictest mathematical terms, F equals ma is like not well defined. What else did we say? Sort of like, in reality, you know, these are not quite infinite, but they're still like super fast and super tall spikes that are like kind of beyond the range of sample rates that we can reasonably do and stuff like that. So it's still a problem. What else should we say? So yeah, and basically all of this makes modeling simulation all the things you want to do. Simulation, control, learning. Hard. It makes everything hard. Okay, so hopefully that makes some sense. There's some like just hard stuff in there. So now like do a little survey of kind of ways people deal with this. So there, I would say there are basically three broad categories. Okay, so let's see. First one, I would call smooth contact models. And so the sort of, it is what it sounds like. What you try to do there is, so usually these are done at the F equals ma level. And what they are doing is essentially going in and trying to smooth out all the discontinuities with some continuous smooth force law. This is a very common technique. You can code this up yourself and be kind of dumb about it, and it'll kind of maybe work. You know, you can imagine doing various flavors of like spring damper models and things like this. The most well-known implementation of this is probably MuJoCo. This is what MuJoCo does. It uses a kind of slightly fancy smooth contact model based on solving a little optimization problem. You can kind of think about it as like a potential function. And there's several papers on this from about 10 years ago, but at the end of the day, it's a smooth contact model. So let's write some stuff about this. Smooth all the contact forces. At the end of the day, these are all some flavor of like nonlinear spring damper model, or can be thought of that way. Okay, so sort of pros here. This is easy to implement in general. You know, you can make very fancy ones, but at the end of the day, you're just like kind of replacing all the bad stuff with something that's like, you know, some F equals ma. You got some force as a function of distance from the surface or whatever, and you can just kind of plug that into your usual dynamics and integrate. The other nice thing about these is that because of the smoothing, everything becomes nice and differentiable, and you can take lots of derivatives, which is convenient for doing control, right? You can like get your Jacobians and all that good stuff and do all your usual control stuff. Same for learning. This smoothness makes doing RL nice, which is why Mujoko got so popular in OpenAI Gym, and all the RL demos were done this way for like a decade, right? Cons of these things, not very accurate. And when I say accurate, specifically, we're talking about the contact dynamics. So you could have a very, very fancy, sophisticated high order integrator, but when you're doing this kind of stuff on the contact forces, you're going to get interpenetration. So you'll get like, the robot's foot sinking into the ground several centimeters, things like that. And you'll also get creep. So you get interpenetration, you'll get force at a distance. So you'll get forces off the ground before the foot touches the ground. You'll get sinking into the ground. And then when you try to simulate stick slip behavior with friction, turns out with a smooth model, you can't actually ever get real stiction. So if you have like a object sitting on a ramp, it'll always creep. It'll always slide a little bit. You'll never actually get sticking friction. So we call that creep. So those are kind of and then the other big one is that the more accurate you try to make a soft model, basically the more you crank up like the stiffness and damping of this spring damper thing or whatever. What do you think happens there to the ODEs? They get very stiff, right? So this is kind of the key problem with these things. You can smooth everything, get ODEs, simulate it like you normally would. You'll get these creep and interpenetration artifacts. If you try to make those go away, you end up having to crank down on these like stiffness parameters in the model, which makes the thing, better and better approximate the true hard answer. But then the ODEs become really stiff and like almost impossible to integrate. And you end up with all the kind of stiff ODE problems we talked about. So you end up having to take really, really tiny integrator steps, use fancy integrators. So this is one of the reasons a lot of these simulators end up taking like 2 kilohertz time steps. It's because if you try to make the contact more realistic, the ODEs get too stiff, and then your Runge-Kutta method sort of starts to barf at you without taking uber tiny time steps, which is very inconvenient also. That said, people have been using these things for a while, and like there have been some successes and some nice results. The biggest issue though is I would say like these issues are basically the source of the sim to real gap. Whenever you hear sim to real gap, it's probably someone from RL talking about Mujoko and talking about like basically these issues and the fact that these, policy trained in Mujoko does not transfer to a real robot very easily. So people end up having to do various kind of transfer learning things to try to get the things to like, take some data on the real hardware and try to polish these things up so they actually work. And yeah, the biggest example here, Mujoko, is kind of the state of the art implementation of these ideas. Cool. Smooth contact models. Any questions about that? Okay, so that's one. The other sort of, I'd say the next one, which is also super common in kind of engineering stuff, are hybrid or event-driven methods. So these methods basically like embrace the discontinuities. And what they essentially do is try to model the smooth dynamics of the robot with a set of ODEs like you normally would, and then explicitly detect impact events, say. They explicitly detect these discontinuous events using what's called a guard function. And then, so like, for example, the guard function for a legged robot would be when the, end of the foot like hits z equals 0, right? So you'd have this guard function that you're constantly checking as you run your simulation. As soon as you hit that guard condition, like height equals 0, you then go and run this other function called a jump map that actually models the discontinuity explicitly. So in the falling brick example, I'd have this guard function that detects the impact event when the height equals 0. Then I go and stop running my ODE integrator, like I'd stop my Runge-Kutta solver, and I'd go out to call this other function called a jump map that would go apply this discontinuity to the velocity and whatever else is supposed to happen, and then go back to the smooth ODE, right? So it sort of explicitly detects the discontinuous thing, goes and executes another function to do this jump, and then goes back to integrating a smooth ODE after the jump. Does that make sense? Does that jive with your experience? Yeah. Okay. Um, So these guys, really double down on the, discontinuous stuff and explicitly model it out. So kind of pros, cons. Let's see. So these, a nice thing about these is you can use standard ODE tools like, adaptive Runge-Kutta methods, get high accuracy integration, all that stuff's good. You don't get stiff ODEs, right? Because you've kind of removed all the nasty stuff from the smooth ODE and you kind of separate those out. So that's nice. And then it also kind of captures I would say this captures qualitatively correct physics, right? So like the smooth stuff, you get all this weird artifact stuff like your foot sinking into the ground and forces at a distance and creep. You don't get any of that here. So it's sort of, in the rigid body limit, this is kind of doing the right stuff. So some good things there. Cons here, the biggest issue with these methods is that they scale very poorly with the number of contacts. So the more contact points you have, the more potential contact configurations you have, the more conditions you have to check for like, is this thing in contact or not? Is there an impact event here or not? So these things are really popular with like legged robots. So quadrupeds, for example, where you have 4 feet and that's kind of it. And you can explicitly check for all that stuff, no problem. So point feet, excellent. If you're talking about like manipulating some complicated geometric object in a hand where there's really an infinity of possible contact configurations there, I can like grip it a bajillion ways and the geometry is really complicated, then like the number of possible contact modes just blows up and it becomes nearly impossible to do this in practice. So good for like 4 point feet, bad for like continuous contact geometry with a complicated hand and whatever. So I would say these are very popular for legged locomotion, not very popular for manipulation kind of stuff. And there's also some weird things in here. So you can imagine like if I have simultaneous impacts where like 2 of these things get triggered at the same time, you can get weird stuff. The other thing that can happen, there's this so-called Zeno's paradox. If you haven't heard of this, maybe look it up. You can end up with like, in the theory here, depending on how you implement these things, you can get like, essentially like, if you imagine a bouncing ball that's like losing height, the time between bounces gets quicker and quicker, right? If I start up here and then I start like getting lower and lower, it starts to do this, right? So theoretically there in the math, if you model it a certain way, you'll end up with like an infinite bounce frequency before it sort of ever settles down. And that can happen in these methods. And that's called Zeno's paradox. And it can do weird things. You also have to you have to think about some weird mathematical issues with these sometimes. You just have to be a little careful with how you implement them. And then the last one is these are not differentiable, right? They're sort of explicitly non-smooth, right? They're like embracing the non-smoothness. So there are things you can do here, and particularly Aaron Johnson's group here has worked a lot recently on differentiating through these hybrid models using this fancy math thing called a saltation matrix. So you can do some things, but sort of out of the box, if you make a simulator like this, it's going to have these hard discontinuities in it, and it's not going to be easily differentiated. Okay, thoughts, comments? Oh, yeah. So these, there actually isn't a general purpose simulator that like works like this, partly because it's doesn't scale. So if you want to simulate some complicated, manipulation thing, this doesn't work really well. They're really popular in control though. So like most of the people doing legged robot control use stuff like this. Yeah, do you have some thoughts too?
So the ODEs don't get stick here.
Mhm.
Is there still going to be kind of an upper bound of the steps that you take just by nature of having that?
Yeah, so the way these typically are implemented is with, so like you can do this, for example, but so we've been using this differential equations.jl toolbox for a lot of this stuff, which does like fancy adaptive step size stuff. That toolbox actually has functionality for implementing these. The way you think about these is not so much at the ODE step size level. You tend to use like fancy adaptive Runge-Kutta methods, and you implement this guard thing as an explicit function that the integrator checks. And what it'll actually do is if it detects you've crossed the boundary, it'll actually go and solve a root finding problem and backtrack you to exactly, to machine precision where you hit. So that's the way so these, you really think about these in continuous time as like, you have a continuous ODE solution, and then you have this discrete jump event. And that's the way to think about it. To make them work well, you actually have to like basically, you end up stepping across, right? And then you end up like backtracking effectively with what you actually do is set up a root finding problem. And you can do this a number of ways, but essentially implicitly in all these Runge-Kutta methods, like RK4, for example, that we've talked about, what you're doing there is fitting a polynomial spline to the solution, right? So RK4 actually fits a cubic polynomial. So what I can do is I can say, oh, here's my last step. Here's the actual cubic interpolant that the ODE integrator, fit to the solution over this last step. I stepped across, so I know I crossed it somewhere on this cubic. So I can actually like just explicitly write down the cubic and solve a root finding problem on the cubic, right? So and just do Newton's method or whatever, like we've talked about. So that's how these things that's the legit way to do it. And differential equations.jl implements all this for you. So you actually just have to write down the guard function and the ODE and like say go, and it'll automatically do this. The docs for that actually have a pretty good description of like how this all works under the hood if you're curious. Essentially, they have some options, but what they basically just do, they have like a cheap version where you do like linear interpolation, and then they have the legit version which uses the full polynomial interpolant and does Newton root finding on the guard function. Yeah. And this thing, okay, cool. Okay, common in control. So you'll definitely see this if you work on legged robots, for example. It's like how all kind of the state-of-the-art NPC controllers kind of reason about stuff, but they are, and so some of the people who do that stuff build their own simulators that are just for their quadrupeds, say, right? Because there you only have to reason about guard functions for these 4 feet. But in general, if it's a complicated thing with complex geometry and multiple contacts, it gets really, really nasty. So this is called combinatorial mode explosion in the lingo. So you call all these different contact configurations modes, and like the number of those modes blows up combinatorially with the number of contact points you can have, right? And so now if you have like a continuous surface where you could have contacts anywhere, like forget it. You have to like explicitly model it as points and like discretize it somehow, and then it just blows up. It's really bad. Okay, that's that one. Then the third category are so-called time stepping methods, which is kind of the stuff we're going to talk about, I would say, really fits into this category. The overall gist of this approach is that we're going to set up and solve a constrained optimization problem at each time step of our simulator to compute contact forces over the time step such that you're satisfying the interpenetration constraint at the next knot point. So if I have like, just a fixed step size, whatever, H, I have a contact constraint that says, foot's not allowed to go through the floor. I explicitly check the constraint at each time on each knot point, right? Each TK. And at each step, so I'm at TK now, I'm solving for like XK plus 1. I check the contact constraint at XK plus 1. And I have this constraint that says, phi of XK plus 1 has to be greater than or equal to 0, like the foot can't go through the floor, inequality constraint. And I explicitly set that up as an optimization problem, inequality constraint optimization problem. The forces end up being Lagrange multipliers, blah, blah, blah. And I solve that problem to find the contact force that makes sure the foot doesn't go through the ground at the next time step. So that's the gist of how this works. And we will do the details Okay, so that's kind of the gist. There's lots of ways to do this. Pros here are this actually scales well in terms of number of contact points. It scales kind of like linearly in the number of contact points. So you can handle complicated things. No issues with simultaneous impacts or anything like that. And then lastly, this also gives sort of qualitatively correct physics, right? Like I'm explicitly enforcing this constraint at the next time step in an optimization problem. So whatever it spits out, the foot's not going to go through the floor, right? Cons here would be these tend to be the most computationally expensive because you end up having to solve a big sort of constrained optimization problem. And also similarly to the hybrid stuff, these are not differentiable. They're at least not differentiable in the classical sense of like, I can compute a Jacobian, blah, blah, blah. Lots of caveats, similar to hybrid stuff. You can do fancy things to sort of get derivatives out of these, but like kind of out of the box, they're non-smooth. And then these are actually really common in robotics. So some of the biggest, sort of stock simulators do it this way. In particular, Bullet, like PyBullet does this, and Dart does this. So if you go use Gazebo, this is probably what you're getting under the hood, and this is, yeah. Okay, so we're going to focus on this one. Cool. Questions about any of that stuff? Sort of the quick tour of all the things. Yeah. Yeah, so there's these all, so Gazebo, I guess technically Gazebo calls other libraries to do its physics. So actually Gazebo uses Dart, I think, by default. And there's lots of these libraries. The details of how you implement this can vary a lot. So this is at a high level, they all solve some kind of constrained optimization problem to do this. The details can be quite different though. So I will talk about the details now. There's lots and lots of ways you can do it. So in particular, right, these are kind of computationally expensive. So most of the simulators make a lot of approximations to try to speed up the solve times. And some of those approximations result in like some qualitatively bad physics. And we can talk about some of the details. So let's actually like dig into this a little bit and hopefully that'll become clear. Okay, so the way we're going to do this, which is not super standard, but it's the way we've been doing it in the class. It's also more general. So you can derive all of the other stuff in these simulators from what we're going to talk about as basically simplifications or special cases or like linearizations of various things. So we're going to do like the full general version. So that's what we're doing. So first thing is we're going to kind of review the KKT conditions for inequality constrained problems, which is super important here. All right, so here's what these look like. So we got min over x of some f of x subject to some constraint c of x greater than or equal to 0. So we're going to take this guy and we're gonna form the Lagrangian in the optimization sense. This is where this gets really annoying. You have like optimization from mechanics, or so we have Lagrangian from mechanics, and then we have Lagrangian from optimization. So this guy is the, the optimization Lagrangian, the thing with the Lagrange multipliers, right? Closely related, but not exactly the same idea. Okay, so that we get that thing. And now we can write down in terms of that guy, KKT conditions. Okay, so we've talked about these. I'm just gonna kind of rehash. So we get basically gradient of everything equals 0. So we get partial L partial X, which is equal to partial F partial X minus lambda transpose partial C partial X equals 0. So gradient equals 0 of the Lagrangian, right? This thing is called, so people have looked at these before. This is called stationarity. Has anyone heard of that? We talked about this. Stationarity, whatever. Then there's a few more of these. So the next one is we need the constraint C of X to be greater than or equal to 0. This is called primal feasibility. So primal being the X's, right? And feasibility meaning satisfies the constraints. The next one is, in this case, we talked about this when we did, at the very beginning, or when we talked about optimization. In the inequality case, you have a condition on the multipliers. So you have lambda also has to be greater than or equal to 0. This is called dual feasibility because lambda is dual variable, right? And remember, this is kind of because this goes all the way back to this idea that the gradient has to equal 0 in the free directions, right? And so here with an inequality, it's only free, it's free this way, but not this way on the constraint. So this positive lambda thing corresponds to the free space being one-sided at the constraint, right? And then the last one is that lambda times, and I'll write this kind of in a funky way. This has to equal 0. And this is called complementary slackness. Okay, this thing is called, has anyone seen this notation before? Circle with a dot in the middle. Hadamard product, it's element-wise product between all the elements in the vector. So every lambda I times ci, all of them have to equal 0. That's what that means, right? You'll sometimes see it written lambda transpose C, which is also correct, but this is actually what's going on there. I think this is a much better way of talking about it. Okay, and then this whole set of conditions here, this C positive, lambda positive, and then lambda times C equals 0, that whole set of conditions altogether is called a complementarity condition. You'll also see it shorthand written sometimes as lambda perp C of X. So this means all three of these things. You will see this sometimes, just as an FYI. Okay, so this sort of whole set of things, the complementarity conditions, it's basically encodes switching behavior, right? So we talked about it in the optimization context, it encodes on-off switching of active constraints, right? Whether on the constraint surface or not. And you can kind of imagine where this is going. this whole like on-off switching thing ends up nicely encoding on-off switching of contact forces, where you're off the surface versus in contact with the surface, right? So like a supernatural kind of way to do it. So we're now going to apply this to the falling particle thing. Okay, so first thing we need when we start doing this is a sign distance function, which is just the height above the ground, and it goes negative when you are in penetration, right? When the thing's under the ground. So in general, this would return closest points between two objects and their distance. So here it's really, really trivial. We have the ground, we have our point mass, and then this is just, so we're going to use phi for the sign distance function. And in our case, for this simple 2D point mass, it's going to be a linear function. So it's just like going to pick out the z component of our configuration Q, right? Okay. And so to be super clear, phi equals 0 indicates contact. And then phi negative indicates interpenetration, which is bad. We should never have that, right? Okay, cool. So now what we're going to do is write down Lagrangian for this thing. Just with gravity. So we've got, now this is the mechanics Lagrangian, which is very annoying. So this is just 1/2 mv squared. And in this case, looks like this. And then we've got mg times the height, which looks like this. All right, everyone cool with that? So I'm going to do the usual thing. I'm going to like that we've been doing with all this variational integrator stuff. I'm going to take this guy. This is the continuous time Lagrangian. I'm going to discretize this in time and get this discrete Lagrangian thing. So it's going to be now qk plus 1. And I'm just going to evaluate that thing at the midpoint of my time step and multiply by the step size h, right? So it's like a little midpoint approximation of this guy. So I'm going to average the positions. And I'm going to finite diff the velocities. Cool. So we've done this a bunch, right? Okay, so now we're just going to write down the least action thing that we've been doing. And we're going to tack on the inequality constraint that says we're not going to let the thing go through the floor. So here's what that looks like. Okay, so we get, just like before, this kind of min over the trajectory of the sum over these little discrete Lagrangian guys. So this is just approximating the action integral, right, over Q of t using this like midpoint rule. So that looks like that. And now we're going to, the only difference is this guy now. So we've got phi of qk greater than equal to 0 for all k. So this looks just like the constraint stuff we talked about last time where we had joint constraints. The only difference is last time we had C of Q equals 0 for all K. Now we have this guy greater than or equal to 0 for all K. Otherwise, pretty much the same deal. And we just turn the crank on this, but we do KKT conditions now. So we get all the inequality baggage. So like last time, I want to also point out here, we're only checking this guy on the not points, right? So when we talked about this in the equality constraint case last time. So like, if you take really big time steps, in theory, right, this guy can have interpenetration between not points, right? So if I check at QK plus 1, these guys can both be on the manifold, but like it's entirely possible that between time steps, there was something that happened, right? It's really hard to kind of like deal with that in general. So this is kind of the best we can do. And what this kind of does practically is sort of maybe encourage you to take smaller time steps if you're getting a lot of that sort of behavior. Okay. So now I'm just gonna write down, so we can do this. It's like literally exactly the stuff we did last time where you like, take the big derivative, play with time steps, blah, blah, blah. All that's the same as when we did just joint constraints. The only difference between that and this is you're gonna get the exact same joint constraint sort of stuff, discrete Euler Lagrange equation, plus these extra complementarity conditions that are associated with inequalities, right? So I'm not gonna do the whole thing again. I'm just gonna write it down from last time and then tack on the extra stuff, if we all agree that that was somewhat painful and not that fun. So we get these KKT conditions. And yeah, let me write them down and we'll talk a little bit. So this is exactly the same as last time. So no big deal here. Oh, and this is this little LD guy. So exactly the same, also the same. I'll explain what this is in a sec. Okay, so you get this. This is exactly the same as last time, where this is like your constraint Jacobian stuff, right? And then we get the complementarity condition. So we're going to get primal feasibility. We're going to get dual feasibility. So I'm calling the Lagrange multipliers N, which is for a very obvious reason that will become very clear as soon as we start talking about this. And then I'm going to get this guy, this complementarity slackness guy. Okay, so let's like interpret all these now. So one thing I'll also note is look at the time steps in here and pay attention, right? So here in this equation, the idea is I plug in QK minus 1 QK and I solve this for QK plus 1, right? The next time step. And I want to enforce the constraint at the next time step. So that's why this guy's evaluated at QK plus 1. But the force is getting applied over the time step leading up to QK plus 1. So this Jacobian ends up getting evaluated at QK. Cool. Okay, so that's what's going on there. And if I look at these KKT conditions, these are the exact same KKT conditions I wrote down before for general optimization. Here, it's just the variable, the letters have changed, right? So let's interpret these though. So this first one, this says stay above the ground, right? No interpenetration. How about the next one? Anyone have thoughts on what the physical interpretation is of the next one? Yeah. So this says, oops. This next one says, so N, I called the Lagrange multiplier N because in this context, this ends up being the normal force, right? Or normal impulse, technically, or this actually is a force because I pulled the step out. Okay, so this says that the normal force that the ground exerts can only push up. The ground can't pull down on you, right? So this makes intuitive sense. And what's this last one say in terms of like physics? That's exactly right. So this says you can't have force at a distance. It says that I can only have a non-zero normal force if the height is 0 and vice versa. So if the height's 0, I can have a normal force. If the height is non-zero, then the normal force has to be zero. So no force off the ground. So all this makes like super intuitive sense. I would say like this is very clean and like, you know, sort of feels right. This is stock optimization stuff out of an optimization textbook. Like literally all I did was plug in like least action and like inequality constraint. And this is just what falls out from writing down the KKT conditions. All this is like very basic intuitive physics. And this is just the F equals MA plus the contact force, right? From last time. That's neat. So for the record, the original paper on these so-called time stepping methods is from the late 90s by these guys, Stewart and Trinkle. And literally the paper just has this giant mess of like complementarity conditions in it that they somehow like pulled out of the ether, out of nowhere. It's just like, where did they get this? And here it's like super clear, it's just KKT conditions from that optimization problem, right? Okay, so let's see, we're almost out of time. Let's just finish up on this. So hopefully this is like makes sense, clean, cool. How do I solve this problem? Thoughts on that? Anyone? Okay, so I can write down this problem right here and like use normal methods for solving inequality constrained optimization problems. The best way to do this, you know, there's always whatever, is probably with a primal dual interior point method, which is like standard optimization stuff that like, so IPOpt developed by Larry Beekler's lab in Chemi, excellent at this. That's what we're going to do in a second. I'll show you the code. So yeah, probably interior point method, blah, blah, blah. But we're going to sort of not do that because it's a lot of extra explanation of how those work. And it's basically for an optimization class that we're not going to cover in here. So we're going to do some hacky stuff. I just want to point out some like quick things before I show you the code. So that complementarity condition, these last three, let's think about what the feasible set is for that guy. It's not good is the short version. So if I have like, so in this case, right, this would be like plotting phi versus n. The feasible set for this guy is what? It's the axes, right? It's like the L, it's this, right? So the original complementarity stuff as written, these both have to be positive. So it's only, and it's like one can only be non-zero if the other is, you know, vice versa. So it ends up being that, which is terrible because it's got a corner in it, right? It's pretty bad. So what we're going to do, it's particularly non-smooth, right? So this is bad. So the message is you actually can't just write those down as they are and then like solve them with an optimization solver. You have to do something to like smooth them, relax them, etc. We're going to do basically what interior point methods do. So if you've heard of primal dual interior point methods, this is sort of a key trick, but we're going to do it in a very kind of like hacky way. So don't quote me on this. It's not like how a real solver works, but this is kind of the key idea. We're going to basically relax this by sticking slack on that complementarity slackness. So instead of strictly equals 0, we're going to put a little s over here that's non-zero. And what that does is take this sharp corner and like relax it out into this kind of like smooth curved region. And the math for this looks like this. This is basically what interior point methods do. They just have like fancy techniques for how you crank down the slack, which we're not going to talk about because it's complicated. So you take this guy and you turn it into n times phi. Right now, we're going to do it like this. So we say it has to be less than or equal to some s where s has to be positive, and that defines this green region, which is smooth and has an interior and all that kind of stuff. Okay, cool. So before we break, let's like actually do this. Here's the code. Should work. Was freshly debugged and tweaked last night. Work with the latest package versions. Also for the homework. So let's see. Okay, we're in business. Okay, here we go. So here's what we got. Mass one, gravity, 20 hertz time steps. I'm going to simulate this for a second and a half. So it's like 30 time steps. Initial conditions, we're just sitting up off the ground with some forward velocity. So this is in 2D, point mass. It's going to be 3 meters high with 1 meter per second to the right. That's, X naught, Q naught, V naught, right? Cool. This is me just doing really dumb, integration to get a Q1 to bootstrap my integrator because I didn't write out all the, discrete Legendre transform nonsense, but whatever. Okay, so then here's my phi, really simple, right? I just return the z height out of the Q, and then here's my Jacobian. I just wrote it explicitly. It's literally 0, 1, right? So it's just picking out the z height of this guy, so that's nice and easy. Here's the stuff that we've done a bunch of times at this point, discrete Lagrangian. So here's the Lagrangian, the original one. Then here's the like midpoint discretization thing. Then here's the derivatives, which I just compute with forward diff. Here's that discrete Euler-Lagrange equation with the contact force stuff, just like we wrote in the notes. This is a bunch of mess, which is just boilerplate code for calling IPopt, which is like the solver we're going to use. It's exactly the same boilerplate as what's in the homework, and you don't have to worry about this at all. So this whole block, just ignore. It's just like a bunch of crap that you have to do to like call the solver through its API, which is quite nasty and annoying. But there's nothing actually like deep or interesting in here. Just be glad that someone else did that for you. Specifically me last year, and then last night it took me like 2 hours going through the docs to update this because they changed the API. Okay, then so yeah, here's like the actual stuff. So this is the objective function. What we're doing here is I have just the slack, and I'm minimizing the slack. So I set it to like 1 or something to start out with, and what I'm trying to do is crank the slack down because the slack is actually adding like force at a distance weirdness to this, right? Then I've just got this Euler-Lagrange equation stuff that we talked about, and then sign distance, this relaxed complementarity stuff. I'm just putting it all in there as a constraint, like we just wrote down. That's it. And now I'm going to solve it. What I'm going to do here is just solve it at each time step. Like, so it's one little problem per time step. Again, if you were to do this for real and make your own simulator, you would basically code all this solver stuff up yourself and make it super fast. This is going to be really slow, but I mean, it's still real time, but it's, compared to what it would be if you were doing this, like, or maybe it's like, took like 5 seconds to solve a second and a half or something, right? It's not great, but that's not the point. Okay, so I'm going to plot the solution. We'll just take a quick look at this. So this is like the X and Y components. This is like the first time you run plots in Julia, it's super slow. Okay, so fine. This is doing what you expect, right? It's just, so there's no friction here, right? So it hits the ground, but it keeps sliding because I had some X component of the velocity. Here's the Z component. This is exactly like the plot we drew at the very beginning of the lecture. Falls, hits the ground, slides. And this is where the impact is happening, right? Here's the impact forces. So I plot that N. So, right, remember what it is in real life, it's a super skinny, super tall delta function spike. But what happens in the simulator? I'm taking 20 hertz time steps, right? So it basically gets, the other kind of interesting quirk here is, right, I never actually resolve the exact impact time. I just know during which time step it happened. So if I'm simulating at 20 hertz, all I know from this is that somewhere in this time step, so like, I don't know, like time step, 19 or something, I hit the ground, right? So this is that spike, but like, notice it's finite, right? It's finite because I'm basically smearing that impact event out over 120 hertz time step, right? That's kind of what's happening. So I only ever resolve it to within whatever my time step is. This is unlike the hybrid methods, right? The hybrid methods, I have to do this root find thing and find the exact impact time. Here I don't, but I just know that it happens sometime in that like 0.05 second window, right? Okay. So that looks good. And then the last thing I want to show you is I played this game of like just throwing the slack into the objective function and minimizing it. And just to show you that this kind of works out, basically this works to, within the solver tolerances that I specified. So this is down, 1e minus 6, 7 or level, which is, I set the solver tolerances to 1e minus 6. So that's cool. Okay, that's it. I'll post the code. Something like this, but more complicated is on the homework, right? I made you do a brick in 3D. But otherwise, this is kind of it. Yay, we did it. Okay, thanks, guys. Catch you next time.